Me to go over any homework questions? All right. Well, today I'm just planning to spend the day putting problems up, letting you work through them, and then I'll go through them. We'll sort of do it step by step, and hopefully you'll just get more comfortable with these 1D kinematics problems. So the first one so this is like, I don't know, do they still have circuses? Is that still a thing? There's like this thing at the circus called the human cannonball, where they have like a person inside a cannon looking thing. And they launch the person, into the air, and they land in a net. So for a human cannonball, needs to go from rest to a speed of 15 meters per second over a distance of 1 meter. And the question is, what's the acceleration? So the path that we're talking about is kind of like the path inside this cannon-shaped thing. When the spring or whatever's launching them is compressed, they're going to be at rest, and then it's going to uncoil, or they're going to be launched by some other means, and by the time they've traveled a meter, they need to be going 15 meters per second. Okay, so see if you can work through this problem. Talk to each other as you go, compare answers as you go, ask me questions if you have them as you go, and then I'm going to go through it and you can sort of compare your work to what I do. Okay, so go ahead and get started. So first of all, I like to just draw a diagram of what's going on. So we're talking about the path of the person's center of mass from here to here, and we know that that distance is 1 meter. Okay, at this point, they're at 0 meters per second, and at this point, they're at 15 meters per second. The first thing we have to do is make those 4 choices. We have to put our 0 position sticker somewhere. We have to decide what's positive and what's negative direction. And then we have to choose the 2 stopwatch instants. I think most people probably would choose their 0 position there when the person's at rest, and their positive direction in the direction that the person moves. You don't have to do that. You could do this problem perfectly correctly with different choices. You do have to choose the right time equals 0 and time final instance, though. So time equals 0. Remember, we're choosing these at instance where we have information and where we want to get information. Okay. The earlier of the places where we have information is when the person starts accelerating. So this is where the instant when the acceleration starts. And time final is the instant the speed reaches 15 meters per second. Anybody have any questions about those choices? So, I try to just keep mentioning, you can have different choices of the position and direction things, but you can't usually have different choices of the times. Those instants have to be the choices that you make. And now we're going to go through the list of variables and figure out which ones we know and which ones we want. Do we know what the stopwatch says at the end? No. Are we looking for that? No. Do we know the acceleration? No, that's what we're trying to find. Do we know the position at time 0? Yeah, that's what I chose as 0 position. Do we know the position at time final? Yes. So we know that at time final, the person is 1 meter in the positive direction from 0. So that has to be positive 1 meter. Do we know the velocity at time 0? At time 0, the person's at rest, so that's 0 meters per second. And then finally, do we know the velocity at time final? Yep. So we're given a speed. And the way I like to think about it is, so it's going to be either positive or negative of that speed, 15 meters per second. And then is that velocity in the direction we chose as positive or negative? Positive, so we'll take the positive one. And now we're looking for an equation that'll let us solve for A. And the one that should work is 2A times the quantity PF minus PI is equal to VF squared minus VI squared. And so 2A times 1 minus 0 is equal to 15 squared minus 0 squared. So 2A is equal to 225. And so A is equal to 112.5 meters per second squared. And I always recommend once you calculate a velocity or an acceleration, think if that makes physical sense with the problem. So the velocities through this whole interval are positive, the way we have it set up. We got a positive acceleration, which means the person would be speeding up. Does it make sense that the person's speeding up over this interval? Yeah, so that checks out, and that's a good sign. The next thing is, will this person survive? That's a pretty big acceleration. I mean, people can survive that. I'm not sure how well his knees would be doing after that, that might be a little higher than I would like. So this is the kind of calculation they would do to say maybe let's just shoot for 11 miles an hour or something, or 11 meters per second, maybe it would go better. But when people talk about accelerations, you hear about it in terms of G's, numbers of G's of acceleration. 1 G is 9.81. So this is, divide this by 9.81. And you get about 11.5 G's. So that's my reaction to that. I'm going to think maybe we don't have to shoot him over the elephants or whatever. Maybe just a little closer, Anybody have any questions about that one? Okay. So I'm just going to keep going with these. For the next one, let's say that an object moves to the right with a constant speed of 20 meters per second for a total of 15 seconds. How far does the object travel? Okay, well, I want to point out that this is a calculation that you've done before, you know, like you kind of have an intuitive idea of how to do this, and your intuitive idea of how to do it is probably right. But I just want to show that in a simple case of constant speed motion, these constant acceleration equations reduce to the way you would do this calculation. So I just want to show you that. All right, so take a second and see if you can work through this calculation. And like always, feel free to talk to each other, talk out loud, hum softly to yourself, ask me questions, and then I'll go through it after I give you a little time. All right, so to get this answer, I mean, all you do is multiply the 20 by the 15 and you get the answer. But I just want to go through this following the steps that we've laid out and just show you how it reduces to this thing that you kind of naturally do in your head. So we have a motion that goes from here to here. We don't know the distance between those two. We know that here the person's going 20, or the object's going 20 meters per second. Here the object's going 20 meters per second. And we know that the total elapsed time is 15 seconds. I'm going to start out by choosing a 0 position in a positive direction. I'll choose my 0 to be here and the positive this way. That means the negative is this way. And so what we're trying to find is the position when the person gets to that second point. And the time equals 0 is going to be at the start of this motion. And the time final is just going to be 15 seconds. And so now I can figure out what variables I know and want. So time final we know is going to be 15 seconds. Do we know the acceleration? That's kind of the key to making this work. Remember that in one-dimensional motion, these two things are like synonyms of each other: constant velocity and 0 acceleration. This has a constant velocity, and so the acceleration is 0. Okay, one always means the other. They mean the exact same thing. Do we know the position at time equals 0? Yes. Thanks for the help. 0 meters. Yes? Oh, yeah. Do we know the position at time final? That's what we're trying to find. Do we know the velocity at the start? Yeah, velocity is equal to, what did I say? 20 meters per second. Okay, and then here's something this can be sort of like a pitfall. So we know that it's constant velocity. We can write that one of two ways, I guess. We can write it as the acceleration is 0, or we can write it as the final velocity is the same as the initial velocity. If we do both of them, it's going to make it look like they're equations that are going to work that aren't going to work. And so I'm going to leave the final velocity off of here. Like what we know is the acceleration is 0. We don't know that the final velocity is 20. Okay, I could have done it the other way too, leave the acceleration off and write v final is equal to 20. Okay, so now do we have an equation that'll solve these? The one that should work is p final is equal to p initial plus v initial times time final plus 1/2 a time final squared. So we have p final is equal to 0 plus 20 times 15 plus, since acceleration is 0, this whole thing goes away. And now you see what you kind of knew intuitively is that to get that final position, to get that distance, all we had to do was multiply the speed times the time. And so what we get is that p final is equal to 300 meters. Any questions about that? So, okay, there are always times in this class where people on tests and stuff use distance equals rate times time to calculate something. Distance equals rate times time only works for one-dimensional problems where the acceleration is 0. Okay, and that's what happened here. We canceled out the acceleration term and it reduced to distance equals rate times time. But be careful with using that form. I think in this class, it's always a better idea to go through like the steps of the constant acceleration equations. Okay, and if it works, it'll come out, like in this case. If it doesn't work, it's because you have an acceleration term there. Okay, the next one. So let's say that an object is launched straight up with a speed of 8 meters per second. From a height of 2 meters. So 2 meters off the ground. So the first question is, how high is the object at its highest point? So let's first go through this one, and then I'll go on to the second one. So just go ahead, take a few minutes and try to figure out how high the object is at its highest point. If I draw a picture of this, it looks sort of like, so this object is launched from a height of 2 meters, and it goes straight up in the air, reaches the highest point, and then comes straight back down the way it came. And we're trying to figure out this height. We have to start with those 4 choices. I always choose my 0 position at the lowest point that occurs in the problem. So in this case, that's the ground. And I always choose my positive direction to be up, negative to be down on these one-dimensional free fall problems. And now, what instant do we want to choose for time equals 0? What's the instant we turn the stopwatch on? Yeah, just the instant that it's launched, right? And what's the instant that we turn the stopwatch off to look at it? Well, so when it reaches the highest point, that's right. So anytime, like, yeah, you're always choosing it based on where you're given information and where you're trying to find information. For part A, it asks us something about the highest point, so that has to be one of those two instants. So time final is the instant it reaches the highest point. And now we can list out what we know and what we want. Do we know how long it takes to get to the highest point? No. Do we know the acceleration? Yeah, in free fall problems and projectile motion problems, we always know it's downwards at 9.81. Do we know the position at time 0? We do. So I have it set with my 0 at the ground, and it's 2 meters in the positive direction from that 0. So this initial position, is positive 2 meters. Do we know the final position? No, that's what we're trying to find. Do we know the velocity at time 0? 8, yep. And so I like to think of this as we're given the speed, and so the velocity is plus or minus the speed, and then we have to think about the direction it's moving. Is it moving in the positive or negative direction? Positive, I chose my positive to be up. And then the last one, the thing that you always use in any question about the highest point, what's the final velocity? 0, yep. There's only one equation that could possibly work because we don't know time and we're not trying to find time. And so hopefully this one works. Otherwise, we're going to have to go back and find another variable. We're looking for PF. That's in the equation. And then we know A, we know PI, we know VF, and we know VI. So this one will work. So we have 2 times negative 9.81 times the quantity P final minus 2 is equal to 8 squared minus 0 squared. Nope, I did that backwards. V final is 0. V initial is positive 8. And so negative 19.62 times the quantity PF minus 2 is equal to negative 64. Remember that that negative is always outside of the square. Otherwise, your answer will always be wrong because you'll lose that negative when you square it. Okay? And so PF minus 2 is equal to 3.26 meters. I'll leave the units off for now. Add 2 to both sides. And that final height is 5.26 meters. 16 feet or something. Any questions about that?
I have a question.
Yeah.
A little bit of a stupid question.
Yeah.
Don't you have to actually do plus 19.62 on both sides?
I divided both sides by 19.62. So it's like, this is like, you know, if you have 5a is equal to 15, you know, where the a is taking the place of these parentheses.
Oh.
And so I divided both sides by 5, but I divided by 19.62. Any other questions? Okay, so that's part A. So now let's go on to part B. And that says how long, and I'm talking about in time, is the ball in the air before it hits the ground? Okay, so let me just say something about this one. If you use, for like a part B, part C, whatever, if you're using the same time equals 0 and time final instant as in the previous parts, then you can use all those same variables that you knew before. You don't even have to think about them. They stay the same, okay? But you do always have to ask yourself whether you need to change the meaning of a time equals 0 or a time final for a part. So on this one, do we have to choose a new time equals 0 or time final instant? We do, because it's asking us about something, about an instant that isn't one of our previous ones. So we just don't have a choice. We have to choose a new one to match this instant. Okay? So go ahead and see if you can work your way through this problem. Okay, let me do this one. So this time, like I said, we have to choose a different time equals 0 or a time final. We can keep the same time equals 0, so I guess I'll still have this the instant that it's launched. We want to find the elapsed time from the instant that it's launched, so if you chose a different time 0, it would sort of complicate things. But time final, we're going to change to the instant that it reaches the ground level. And so what this means is all of our initial value stuff is going to stay the same, but our final value stuff is going to be different. We're trying to calculate how long it takes, so time final is what we want. The acceleration, it's still in free fall, so this is still negative 9.81 meters per second squared. Our initial position is still positive 2. Our final position is ground level, and that's what we chose as our 0, so P final is 0. And our initial velocity is positive 8 meters per second. And we don't know what the velocity is the instant it reaches that level. It's going to be down at some velocity a little, it's going to be negative 8 point something probably. Okay, so the equation that should work here is P final is equal to P initial plus V initial times time final plus 1/2 A time final squared. And anytime you use this equation to calculate time final, you're in extreme danger of having to use the quadratic formula. Sometimes you get lucky and some things are zero, but in this case, we're going to have to use it. So P final is 0, P initial is 2, plus 8TF, plus 1/2 times negative 9.81. I'll just write that as negative 4.905 TF squared. Okay. So we have to use the quadratic formula for this. This is A in the quadratic formula, the one that's the coefficient for the squared variable. This is B, and this is C. So plug that into the quadratic formula. And it gives you two solutions. Okay, and the answers I got are negative 0.22 and 1.85. Okay, well, we have to choose one of those over the other one. If you're using the quadratic formula to calculate a time, this choice is easy because we'll never see negative times. We're starting all of our stuff at time equals 0. And so we can just get rid of the negative, and that means that the elapsed time is this. Okay? Anybody have any questions about that? And what does that negative 0.22 mean? Well, it means that, so if you think of a position versus time graph of this motion, this thing starts at 2 meters at time equals 0, and constant acceleration motions for free fall in 1D always look like parabolas. Okay. But the math doesn't know that this object hits the ground eventually, and it doesn't know that at some point it was launched. This should be symmetrical looking, by the way. It sort of looks a little tilted, but that's just the best I can draw it. According to the math, this whole thing that goes on infinitely far in the negative and positive direction is all valid stuff. And so the negative 0.22 is the time when this parabola crosses that 0 position on the way up, before it was actually launched. And then there's all this stuff that would happen if the ground wasn't there and it just kept going forever. So this is where that negative time comes in. If you ever do a problem where the thing is launched from below what you're calling position equals 0, like if it's launched from a hole in the ground, a meter below the surface, you're going to get 2 positive times. One is going to be when it reaches the height of the ground on the way up, and the other one is going to be when it hits. And then you have to use that information and think about which one you want to give the right answer. Okay, I want to do one more problem. I'm not going to do multiple parts on it, but this has two more things that I want to make sure that you've seen before. This is a helicopter moving straight up. At 3 meters per second. And an object is dropped from the helicopter from a height of 15 meters. What's the velocity of the object when it reaches the ground level? Okay, take a few minutes. So the key thing that you need to notice to start this problem is, remember I said if an object is dropped, then at that instant, its velocity is whatever it's dropped from. So this thing is going to start with an upward velocity. This object is going to start with an upward velocity of 3 meters per second. And so this motion is something like this. It's going to start out at a height of 15 meters, and it's going to start out with an upward velocity of 3 meters per second. I'm going to choose my 0 at the ground, my positive up, and my negative down. And my time equals 0 is going to be the instant that it's dropped. And my time final is going to be the instant it reaches the ground level. We don't know the total time. The acceleration is negative 9.81. The initial position is positive 15. The final position is 0. The initial velocity is 3 meters per second. And we're trying to calculate the final velocity. The equation that'll work here is 2a times the quantity pf minus pi is equal to vf squared minus vi squared. So negative 19.62 times, whoops, I have these backwards. Pf is 0. Pi is 15. And then that's equal to the final velocity that we want squared minus 3 squared. And so you get, what's that, 294.3 positive is equal to Vf squared minus 9 And so VF squared is equal to 303.3. Okay, now is the last thing you have to notice here. We're going to take the square root of this variable. And so you have to remember that that can be positive or negative. So positive or negative square root of 303.3. And you get plus or minus 17.42. And now you have to know what you have to think what you know physically about this problem in order to decide whether you want the positive or the negative. Which of those velocities makes sense in this case? The negative, because when it gets to ground level, it'll be moving down, which is our negative direction. So we want this one. Any questions about that problem? Okay, well, I'll give you something to work on over the weekend, and have a nice weekend.